Okay, good morning, my wonderful students. If you look up here towards the front, you will see some equipment off to my left, your right, that is the Van de Graaff generator. You know, it's amazing the number of people that are not actually looking up here. They're looking at their phones and their computers and stuff. All right. So what we're going to do is the Van de Graaff generator demonstration. And I put a YouTube of the one that they built for Mythbusters. That's on the web courses. You can look at that. But before I do that, I want to talk a little bit about special study group leaders. And a few of you have emailed me or messaged me in web courses about it. Here's the list of students that I've invited from Section 1. 6 students, we just talked to them. Section 2, Danielle Adogi, Mivosh Albersky, Javier Alvarenga, Tatiana Amadeo Floret, Tanner Anderson, David Andrews, Christiana Champnella, Carolyn Cook, Joseph Dunlevy, Bria Fitz, Brian Hutchinson, Colton McFarlane, Tyler Momini, Natalie Olenek, Jacob Paul, Camille Robinson, Ashley Shookman, Sean Tiernan, and Isabella Yerby. And a few of you guys, a few of those students are not here yet. And I know one of them is absent today. What you guys want to do, if you're on that list, you want to double check your inbox in web courses. And in that, you'll find the invitation from me, and you'll find the specs that you will need to execute in order to be a special study group leader. You know, like taking attendance and organizing your session and so on and so forth. It is, for those of you that are on the list and you're here right now listening, it is not required for you to be a special study group leader. It is a request. It is an invitation that you can turn down. And if you feel like you have to turn it down, do not, don't feel, like you're putting me out, or takes no skin off my nose. Every semester, there's 1 or 2 students that say, Dr. B, I just can't swing it between my classes and my, my job off campus and whatnot, or, whatever the reason happens to be. It's all right. So you don't have to do it. If you do, and you execute your SSG leader duties sufficiently, you can skip the final exam. So it's a nice reward for doing that task. Now, the way it works, you guys that are special or going to be special study group leaders, you're going to sign your little PDF form that I emailed you or that I messaged you with in web courses. Print it out and sign it and bring it back on Thursday, and then we'll include your meeting time and place and so forth, and we'll get you on the schedule sheet. And then students on Thursday night will sign up, and then Friday afternoon until Monday night, you'll be able to do your special study group sessions. All right, now you're going to have some questions about how it all works, but let me show you some stuff that you're going to see. Specifically, for the rest of you that are not special study group leaders but want to sign up for special study groups, that's good. I want you to sign up. The first thing that you want to look at is the schedule page. It'll look something like this. This is the schedule page from last semester. And the schedule page is where you'll look and find the schedule, the time, the day, location that fits your schedule. And then hopefully when sign-ups start on Thursday night, you'll be able to sign up for that student's SSG. Now, at the top, I usually have some kind of a distinctive image for you to key on so that you know that you're at the right place, because this is the place where the schedules are, and also right up here, well, in this case, I have a red stapler last semester. I'll use something else this semester. Right here, where my cursor is in the middle of the screen there, that's where the signups link will be. As soon as I activate that, you'll be able to click and go to the signups page. I can't show you the signups page right now, okay? But on Thursday night, hopefully, like maybe 8 o'clock, I'll activate that link, and you'll be able to click through. And if you've looked at the schedule, you'll be able to try to get into one of the groups that you like, right? And always look at the schedule and have maybe 1 or 2 alternates to your favorite, because it's going to be like the Oklahoma land rush. It's going to be a real buffalo stampede on Thursday night. And if I open it up on Thursday night at 8 o'clock, it might be completely over by 8:05. That's how fast it works. All right. Now, there's about 25 students that I've invited. If all of them accept being special study group leaders, that means there'll be 150 slots. Now, that's not enough for everybody, but it's first come, first served, so you just got to be fast. Now, I make it later in the evening, so it's not going to be, like at 3 in the afternoon, because I know a lot of you guys are working. You have class, or you have a job, and plus, or maybe you're working out, and then you got to eat dinner at 6 o'clock, and then after 6, sometimes, maybe there'll be, time for you to sign up. So I'll probably make it about 8 o'clock or maybe 9 o'clock, but not too late, so that, so it doesn't run too late. But be ready to jump. Now, the top of the page is going to have some distinctive image like this. All right, and right below that will be the sign-up link. Now, below that are the schedules. And this is the who, what, when, and where type information, plus a mugshot of each special study group leaders. And it'll show you, okay, here's Lauren Baker, she's number 1. Nicholas Schaffer, he's number 2. And then Zachary Frame, he's kind of out of the frame here. It's just a screen grab from last semester's SSG schedule page. But you can look at that and, think, okay, this person's going to be meeting on Saturday morning. I actually can make that. Okay, so pencil that down. Make it, take a little sticky note and think, okay, group number 1. And then look down the list. And group number 7 might be Saturday right after lunch, and you can make that too. So then group number 7 on your little sticky note. Right? So then when the Buffalo Stampede starts at 8 o'clock, you can check number 1 and then number 7, and hopefully there'll be a spot. There's 7 spots in each group. The special study group leader is always number 1. I put them in there. And then you guys that go into the signups page, you'll elect the special study group that you want, right? Also, if you participate in the special study group, you sign in on the attendance page. Your special study group leader will have an attendance page. You'll get 4 bonus points, as I've mentioned, and so that's good. We'll do it again, 2 rounds. This one coming into exam 3, and then another one coming into the final. Now, for us, we're section 2 here. This is the afternoon section. Your final exam comes up first this semester. I don't know, what is it, Thursday, Wednesday or Thursday of finals week. And the other the morning section, they come later, right? So, that being the case, the second round of special study groups will go from the Friday at the last week of class until the night before the final, right? For you guys in section 2, right? So and all that special study group leaders, potential special study group leaders, all that's spelled out in the email and in the PDF that I sent to you. Okay, it's all specified. Now let me pause for questions about special study groups. Any question that you care to ask? Yes.
So this is the exam 3 sign up and there's a separate sign up.
That's right. The question was, is there going to be a separate sign up for the final? And the answer to that is yes. And you can sign up for, if you go with Lauren Baker and then she might have a different time and place for the second round. And it might not fit your schedule. That's all right. You can choose somebody else that does fit your schedule. You're not married to this person that you select. So just, whoever fits your schedule, that's who you go with. And hopefully there'll be a spot for you when signups activate. Another question? Yes?
How do we get to this page again?
The question is, how do you get to this page, the site? Well, this is the schedule page. I'll put a link to it as soon as I set it up at the top of our home page. All right? And it'll be in color. You'll see it. There's a video there right now with the what do you call those guys? Mythbusters. The Van de Graaff generator that they made. And usually I put emergency or urgent stuff up there at the very top of the page. And this will be the link to this schedule page will be up there. Okay. Another question. Carolyn. You can talk to me in web courses. You can talk to me after class, but I want the PDF that I sent today signed, and I want the hard copy of that. If you don't have your meeting details when you sign it and drop it off to me Thursday, you can message those. So say that you want to have your meeting, you go and reserve a study room in the library, room 423 or something like that. All right. Then you can message me that tonight, and you'll be ready to go, in your time and, distinctive features and stuff. But I still want to get that signed paper on Thursday, so definitely bring that. So, but the more we, just communicate and stuff. Give me the signed printout and then communicate, and that'll be good. All right. Now, I want to point something out to you on this screen here. You might not be able to see it. Did you get your message? Okay, good. And this is for special study group leaders. I always ask them, how will other students recognize you? Because you might be getting students from the first morning section, and they don't know you from Adam and Eve. All right? By the way, did you know what? The special study, there's about 25. And you know what? The majority are women. The guys are slacking. The women are shining through this time. Way more females. Anyways, so the special study group leaders, you're going to want to tell me, how will your students recognize you? Because they might not know you from Adam and Eve. All right, so Lauren Baker here, what she writes, how you will recognize me, pale blue t-shirt, jeans, and white Converse. She's wearing her high tops. And then Nicholas down below there, how will you recognize me? I am a giant guy. He's a big, tall guy. About 6'17" or something like that. Well, not quite that tall, but he was a giant guy. And a black security hat on. All right. So you'll be, so if you tell me, oh, well, I'll be wearing my lucky fishing hat or my favorite blue sneakers, whatever it is, so students recognize you, that'll be good. Another question. Yes, Isabella.
Provide you with a picture, or are you gonna take?
I've already got the mug shots. I've got everybody's mug shot. The mug shots? Yeah, they're going to be on the schedule. You mean for the SSG leaders? You mean you want to see your mug shot? No, that's classified information. I'd have to get permission from the FBI for that and the CIA and the President of the United States. Anyway, so it'll activate like maybe Thursday night. And so you individuals that are going to be special study group leaders, Christina, etc., you'll know who's in your group by sometime Thursday night. All right. Now, I want to turn to physics questions, and we're actually going to do a practice question, special kind. It's a question for which you will generate an answer. I'm not giving you multiple choice options. I'm not giving you a number to calculate. I'm going to give you a chance to answer a question. Now, this question that we're going to do right now, it's a practice question. And as with all practice questions, this one's going to be a Chuck Norris question. All right? So, what I want you to do is turn on your clicker, and you'll be in typing mode, so you'll be able to type in letters. I want you to look at this table, this code table, and form a Chuck Norris fact. All right? So we're just doing kind of a goofy Chuck Norris example for what we eventually will be using seriously. So in other words, the sentence YIVU, sharks are my friends. You type that in and then hit the send key. All right? Now you can be as creative as you want to be. And I think the limit is 14 characters. So you can't exactly write a sonnet, but Tatiana, you can write something interesting. All right? And so, it's got to be more than one letter to be a true sentence. So 2 symbols or more involving Chuck Norris. CADJ. What is that? Chuck Norris, always roundhouse kicks. Justin Bieber, good. We're seeing a lot of Justin Bieber getting his kicked. Although truly he's not a criminal so far as we know. So really he doesn't deserve to be. See, and I can see what you guys are, and you know what, we're going to be doing this in class, for a science question, about the electric field or something, and we're going to be doing it on the next exam and also on the final. So this is just kind of a warm-up exercise. Just type in something good. And the way that this works, you guys, I analyze your answers. I'll turn your code, YIVU, back into a sentence, and then I'll read your sentence and either give you 3 points or 2 points or 1 point or 0 points. All right? So if you typed in something like GIH, left is right, that would be a sentence, but it would be 0 because it's incorrect. Left is left, right is right, and there the twain shall meet. Okay, so that was wrong. But if you type in something like FIR, are crooks or slackers, then I'd give you points for that. Because everybody knows that. All right, I'll give you another 30 seconds. CADR, what is that? Chuck Norris always roundhouse kicks. Slackers. Good. J. Never. Roundhouse kick. Justin Bieber. Whoa. Ooh, somebody wrote a sonnet here. Somebody wrote a sonnet, but it doesn't make a whole lot of sense. I guess maybe it's a Chuck Norris fact. All right, 10 seconds. 10, 9, 8, 7, 6. Hit your send button. Make sure, because it doesn't know you're finished until you hit the send button. 5, 4, 3, 2, 1, 0. Okay. Let's go down in the list. Go ahead. Yeah, switch to the display. Let's go down somewhere in the list and look at. All right, let's look at some of these answers. Go past the C's. See if we get anything. Oh.
Oh my God.
Oh! That's not a Chuck Norris. I don't think it's a Chuck Norris fact.
I don't think so.
It better not be. All right, let's stop there. Let's
Okay,
stop.
yeah.
I can't believe it.
That's funny.
Somebody doesn't like him. I don't like him that much either. So, anyways, JMNPCD. That's a big long one. 6 characters. Let's see. J is Justin Bieber can not escape CD. Chuck Norris, that's right. Justin Bieber cannot escape Chuck Norris roundhouse kicks. Nobody can, for that matter. Okay, let's look at JLVZ. Ooh, there's a lot of Justin Biebers here. JLV. Somebody loves Justin Bieber. What is that? Justin Bieber has my French fries. That.
Oh. See, now he deserves the roundhouse.
Yeah,
kicks.
that's no wonder he deserves a roundhouse kick. Switch back to the regular. JLVZ. See, this is now, and we're just messing around here. So we're just kind of screwing around with this, and it's kind of humorous, but this highlights the fact that you are being creative in what you send. Now, that has a huge advantage for me when I'm asking you a science question, as we will do tomorrow probably, and on exam 3 next Tuesday, a week from today. You'll be writing a correct answer. And if all 100 and whatever of you in here type in a different, did you see how many of those answers there was only one person that typed that in? And that's really the case a lot of times. You know, that people will type in unique answers, and if your unique answer is kosher, if it's good, you'll get the points for it. And I love that because if you think about it, it reverses the psychology of a test. It flips the test around. On a regular test, multiple choice, true, false, calculation, matching. I set it up so that the right answers are in there, and I'm also in control of the wrong answers. Multiple choice, Lexi, I got to type in some wrong answers. I can't, you can't have, a multiple choice with only one option, the correct one. You got to put in some, some tempting, tricky, a little bit trickiness, wrong answers. I'm even in control of that. True, false, the same. Calculation, I'm in control of the numbers and what you're supposed to calculate, so I'm in control of that. Matching, I'm in control of that. But this, you are in control of. How you answer. And you're in control of stating something that I might completely never have thought of. And if you do, and I like it, I'll read 300 and something sentences after exam 3. And I'll be giving you not bonus points, but regular points based on that. If your answer is good. And I love that. That is where you guys are finally getting a chance to be creative. Instead of me, calling the tune every single time. Question?
So would that being said, are we going to get partial credit?
Yeah, you get partial credit. Typically it's a 3-point question. So 3, 2, 1, or 0. Right? But if everybody gets a 3, everybody gets a 3. It's like a calculation. There's one correct answer, and even if I put plus or minus a little bit, plus or minus 0.01 or something like that, then it's still a pretty narrow range of what's correct. But on this kind of question, as rich as language is, as creative as your mind is, and multiply that by 300, that's how many variations there can be, and all of them good. So now most instructors won't do that, but it's something I love to do. So we're going to do this we're going to do some more clicking today, regular clicking, but tomorrow we'll have another code question, and then exam 3 will have a code question, all right, to form a sentence. And they're not going to be like, the English department might not like them. They might not have, because we only have 14 characters to work with, 26 symbols. So it can't be as graceful as, Shakespeare, but it still can be a good sentence, and we'll grade it accordingly. Now, I want to do a demonstration with you up here in the front. This big gold sphere that you see up here is the Van de Graaff generator. And I want to point out to you that for those that are not here listening to this on YouTube, there's a YouTube of the demonstration that the people that are here, you're all going to be able to see. And we did it last hour. It worked really, really nicely. It's in YouTube, and it's from 2010. We videotaped it back to 2010. I think there's another 1 or 2 in there. But it's on the demonstrations playlist. And there's the YouTube address for it. Can you turn the lights up? We're going to do the... Oh, by the way, announcement. It's not in the slides. SI review for exam 2 or exam 3 is Thursday, 4 p.m. to 6 p.m. All right, SI review. Now, I think she has SI on Thursday, regular SI, right? Okay, so regular SI at the regular time, and then SI review for the exam 4 to 6 p.m. Classroom building 2, that's this building, room 106. All right, and I'll put this up in web courses as well. Okay, now I have some clicker questions about the Van de Graaff generator. All right, so what I want you to do now is hit your refresh key. Whenever we go from a code question to multiple choice, or multiple choice to calculator, type in a numeric answer, we have to hit the refresh key. So hit your refresh key, And then here's a multiple choice question for you about, and add this to your notes. The metal sphere of the Van de Graaff is positively charged by design. That's how it works. All right? They suck out the negative charges, and so the positive end is, or the metal end is actually positively charged. What does that mean? Go ahead and vote. See this?
Again.
20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, go ahead and display that. Now look at that. You have a real spread of answers. So let's talk about this. Go ahead, back to the regular display, please. Okay. Okay, A cannot be right. The metal sphere is positive, so it can't have a lot of extra negatives. All right. It could be that B is correct because, okay, if you strip away some electrons, you take away, subtract a negative is like adding a positive. Think of it that way. So that's a possible yes. It's been polarized. No, not at all. It's not polarized. It's still a sphere. Polarized would be turning into an ellipsoid, like an egg shape. That would polarize it. Extra protons have been added to it. NO. I believe I mentioned last time. I'll mention it now if not. Protons are about 2,000 times the mass of an electron. So, in most terrestrial human scale systems, the charges that move are the electrons. Protons usually don't move around at all. Not very much. Right? They're just kind of set there. So they're in the crystal lattice, or they're in the metallic lattice, or whatever kind of, or the molecule itself. So they're not really moving around very much. Static electrical charge neutralizes the metal sphere. Is a nonsense answer. Static electrical charge neutralizes. How can charge neutralize something? Charge charges stuff. It doesn't neutralize stuff. Right? So the correct answer is B. Now, make sure the next question, add to your sketch of if you haven't sketched the Van de Graaff diagram here, the sphere and the little post and the base. That's kind of what we got up here. The post is not yellow, it's clear plastic. By the way, did you hear that sound? That was a little motor, and it was running a little conveyor belt up into the metal sphere and then back down into the base. And the way that it charges up is by friction. And it's set up so that the positive charge accumulates in the gold sphere, as we just talked about. Now, hypothetical question about what a charged piece of styrofoam, positively charged, initially at rest, where would it tend to move? Path A, radially inward. Path B, radially outward. What would it tend to do? Path C, orbiting counterclockwise. What would it tend to do? Path D, orbiting clockwise. Make a sketch and make sure you label especially paths A and B, because that vocabulary term, radially inward, we need to know that. Radially outward, we need to know that. Just, to be able to say, okay, this shape that I'm looking at, Spatially is radially inward, or it's radially outward. So that's a new vocabulary term. Okay, 15 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. We got a range of answers. Here's the correct one. Radially outward. Positive would be repelled by all the positives in the metal sphere. So make a note of that. If you didn't vote for B, make a note. The positives of the sphere would repel the red positive piece of styrofoam. All right, now, you got that sketch? Radially outward path B? Kane, question. Yeah, opposites attract, likes repel. So positive repels positive, negative repels positive. And that's a feature of the electromagnetic interaction. Gravity is not like that. Gravity always attracts. No matter what kind there's no flavor of kilograms of mass. You know, mass is mass and it always attracts. Charge is charge, but sometimes it attracts, sometimes the same charge can repel. Just depends what you're looking at. Now let's look at this. Go ahead and make a sketch. A negatively charged sphere. Now the field lines, the set of paths that a positive piece of styrofoam, this red positive, the red circle with a little plus sign in it, all the paths that it would take are radially inward. Right? And that's if the metal sphere is charged with some surplus electrons, net negative charge. Right? So now the hypothetical positive charge would want to move radially inward. And my wonderful students, the behavior of this hypothetical charge, a positive test charge, is what tells us the direction and the location and even the intensity of the electric field. The electric field lines that I've marked out here are determined by the behavior of this hypothetical positive test charge. But the electric field has an independent existence. It doesn't depend on the fact that there's a positive charge there or not. It is intrinsic. The electric field and the electric field lines are intrinsic to any array of charge, whether a negative charge like this, or the previous slide, a positive charge, or some combination of the two. The electric field lines are intrinsic to the charge array, and they're defined by the behavior of a positive test charge. And by the way, light itself is an oscillation in the electric and magnetic field lines of some source of charge somewhere. Right? So whenever you see a light, whenever you're getting light in your eye, somewhere on the other end of that ray of light was an electric charge of some kind, oscillating back and forth and wiggling its field lines. These are the field lines that it's wiggling. Now, these are static. This is what you call electrostatic arrays. They're static, they're not wiggling. Dynamic arrays that wiggle and move and stuff, they would generate electromagnetic fields that we call light. Right? So this is just like a snapshot of field lines. Now, summary side note. The field lines of a positively charged object, positively charged sphere, go outward radially. The field lines of a negatively charged sphere go inward radially. All right? Positive sphere, outward radial field lines. Kind of like spokes on a wheel, except they're in all three dimensions. So it's like what do you call it? A porcupine or a sea urchin. You know, the spines go off in all different directions. For a negatively charged sphere, field lines go inward, just like this diagram. All right? So that's summary side note. Now, let me show you what happens now when you have a positive and a negative fairly close to each other. When you have them fairly close to each other, here's what it looks like. All right? This is called an electric dipole. The positive and the negative are fairly close, so their field lines are going to interact. Now, here's what you've got. Over here by the negative, the blue negative charge, the field lines, they're kind of, if you're in close, they're pointing straight in. But as you get a little bit to the right and downward, they start, see down here, the field lines, they're not pointing straight back at the positive charge. And the reason for that, it's not pointing back towards the negative charge, the electron, because there's a positive charge over here. Similarly, if you look close to the positive charge over here on the right, the red circle with the plus sign in the middle of it, the field lines are going outward, straight outward. But now, if you start dipping away, like up here in the upper right, they're not going straight away from the positive charge up here. And that's because of the negative charge being fairly close. So the electric dipole, they merge, the field lines merge gracefully. All right, now, what I want you to look at here is the fact that this dipole array has two symmetry lines. So make your notes. Symmetry lines of the dipole array are horizontal, the horizontal symmetry line through the two charges, so right through the middle of this diagram. Okay, and what that means, Kamari, is if you flip top for bottom, the field lines look the same. Okay, the field lines up here, like right up here, they're going to the right. Or excuse me, they're going to the left. Field lines down here, going to the left. They look just, so if you flip-flop top for bottom, yeah, around the horizontal symmetry line, then the field lines look the same. Second symmetry line number 2, vertical and right down the middle between the two charges. So half, vertical, and it's halfway between positive to negative, right? Now, that one is a symmetry line because if you now go, if you fold it left to right, the field lines have the same shape, although the field lines over here are going inward and over here they're going outward. Still, they have the same shape, right? So the shape is symmetric left and right. Now, here's another picture. Try to draw this one, right? This is where you actually see the field lines gracefully merging over from positive to negative. They launch from the positive, they land on the negative. Okay? The field lines launch from the positive and they land on the negative. Where the field lines are close together, Jasmine, the electric field is considered strong. So out here, the field lines are starting to spread out. You're fairly far away. The electric field's fairly weak out here. Now, in close here, whoa, look at right in here. Close to this negative or close to this positive, yeah, Field lines, they're starting to get really concentrated down there, Nicole. So, yeah, you've got a lot of intensity. You're close to the electric charge, so the pull force or the push force is going to be pretty strong. But out here, to the upper left corner, any of the corners of this diagram, it's going to be a lot weaker. And the field lines are not as concentrated. All right? So, all the field lines, they gracefully loop around. Have you ever seen field lines like that before? Where have you seen field lines like that before? Raise your hand if you've seen something like that before. Green hat. Man in the green hat, yeah. Excuse me? Yeah, Earth's magnetic field. Or the magnetic field of a bar magnet. All right? Earth's magnetic field is a dipole magnetic field. This is a dipole electric field. A bar magnet is a dipole magnetic field. All right? Is that what you were thinking, DJ? Yeah. All right? It is not a coincidence. The source of the magnetic field is any charge that's moving. The source of electromagnetic radiation is any charge that's accelerating. Okay. Repeat. The two symmetry lines, yes, two symmetry lines. One of them is vertical, right down the middle. The second one is horizontal, from one straight across the diagram, right through both charges. All right, Taylor.
Another example of those things that are in the store that are globes with like the lights inside that you touch and they connect. Do you know what I'm talking about? Like
No.
little streamers, like the light streamers.
I've never seen that. Where do you see that? At like the store? You mean like at the mall or?
Yeah, like at the mall or anywhere like where they sell like.
Who knows what she's talking about? Streamers and stuff?
The globes.
It's like a circle and it looks like.
It's got like
pretend
streamers
that
and like
thing
the static like attracts it to the so it wiggles.
So
Yeah.
where did you see that? Waterford Lakes?
No, I just remember from when I was little going to the mall with my dad or something. Those would always catch.
Yeah,
my
no,
attention.
yeah.
And you just
Really?
touch them and then they, like.
All right, I want it. Okay,
Here, I'm gonna look it up.
I'm putting an APB.
Streamer.
All points bulletin. Be on the lookout for this thing that Taylor just was talking about. The globes at the mall that they look kind of like this thing, sort of. All right, I want it located so I can go see it because it sounds pretty cool. All right, now we're going to talk more about dipole fields because they're important for molecules. But before we do that, let's get back down to business about charges. And let's just reinforce some of these concepts. We've already talked about this. The charge in matter resides in electrons and protons, as far as we can tell. And we've been studying it for over 100 years. The electron seems to be an intrinsic and unbreakable particle. The proton we can now break apart, but we can't keep it apart. The proton is made of 3 quarks, subatomic particles. An electron doesn't seem to have any structure other than just being an electron. But they each have equal charges but opposite. Electrons are negative, protons are positive. They interact. The charges interact by what's called the electric force, static cling. We've been talking about it. Like charges repel, unlike charges attract. And we're going to show you how that works. Right? Now, I want to go through with you some items of atomic structure, Benji, to go over the idea of an ion. Okay, an ion is an atom that has extra negative charge or extra positive charge. An atom tends to be neutral. Atoms like to be neutral. But it's not necessary for them to be neutral. We can make them negative or positive. All right? Now, the top panel on the left in pink, supposedly that's pink, is a neutral lithium a neutral lithium atom. There's 3 protons in the nucleus. So that's 3 plus signs, protons in the nucleus. The neutrons in the nucleus are not listed. They're not drawn here, so it's kind of a schematic diagram. And then around the nucleus on those 3 circles, those 3 minus signs, those stand for electrons. Okay, so schematic diagram of a neutral lithium atom. Now, if you take one of those electrons, and the easiest one being the outer electron, then you have a net positive charge. You still have 3 protons in the nucleus, but now you only have 2 electrons in orbit, so your net charge is plus 1. All right, so that's what we call positive ion. All right, it's supposed to be raining outside. Now, a negative ion, let's take a look at that. A negative ion, so down here at the bottom now is the pink neutral lithium atom, schematic diagram. And up here in the darker pink, that's a negative ion. Yeah, you can take a neutral lithium atom and kind of shove in an extra electron, and if you do, it'll stay bound to the nucleus. I mean, the force that keeps the electron on orbit is the electromagnetic interaction, okay, that we've been talking about. And you can put another one on there. It will tend to be stolen. Lithium's outer electrons are easy to steal because they're not bound very tightly. They're at a higher orbit, so they're easier to steal. The electromagnetic interaction is weaker out there because the further away you are from the nucleus, the weaker the force. Right now, if you take a negative and a positive, they're atoms, but if they have a net positive and the other one has a net negative, they'll attract each other and they'll bind together. That is called an ionic bond. The most common everyday example of an ionic bond is table salt. You know that you put on your French fries. NaCl, sodium chloride. So make a note, sodium, Na, chloride, Cl. Chloride is greedy. The chlorine atom wants to get every possible electron it can get. This is the way it's structured. Sodium is a weenie because sodium has one outer electron out there. You know, its inner electrons, the inner orbit, yeah, no problem. But the outer one, easily to steal. In chemistry, you would say it's easily oxidized, sodium. So the chlorine steals the electron, becomes a negative chlorine ion. The sodium loses an electron and becomes a positive sodium ion. So Na plus, Cl minus, and they bind together to form salt. That's an ionic bond. It's an ionic compound. Let's talk about conductors and insulators. All right? Now this picture shows a lemon with a piece of copper wire and a steel paper clip jabbed into the lemon and then connected to a wire, and that wire has electricity flowing through it. And the reason I know that is because the wire is wrapped around a compass. The current going through those loops forms an electromagnet, and that electromagnet controls the compass needle, as you can see. That's known as a citrus battery. That's basically how batteries work. All right? In a battery or anything else, electrons that are free to move throughout the material if it's a conductor. All right? So copper has a couple outer electrons that are particularly easy to move. Gold, similar. Aluminum, not too bad. Silver, pretty good. Iron, it's okay. It's a conductor, but it's not, it's not great shakes. You add charge to it, the charge will dissipate. It'll repel away, the electrons will repel. They'll go to opposite sides, and if you dump in some more, they'll just try to squeeze each other out and just equilibrate and move if it's possible. Like the sparks that we saw up here, or that we heard up here. Those are electrons in motion. Examples of conductors are metals, graphite, a form of carbon, and an ionic solution. An example of the ionic solution is the acid inside this lemon. And if you're an elementary ed or a secondary ed major, and you want to do science fair projects, this is a good one. You can do a battery like this, just this exact cinchy looking thing, and it will do it. You'll be able to deflect that compass needle. You can do it with potato. You can do it with a grapefruit. I've done it a million times with grapefruits. Oranges, any kind of citrus, it's got a little acidic fluid in it, but even a potato will work. But you have to have two different kinds of metals. All right, so lemon and copper, steel battery clip, battery, coils around the compass. If current's flowing through those coils, you got another electromagnet, and then the compass needle is a magnet, so they interact and they line up with the coils. Now, the opposite kind of a substance is an insulator. And this is a substance where the electrons, there's some outer electrons, but they're not as easy to move. They're more tightly bound. So if you can drop some electrons in there, they're not going to redistribute very well. They're just going to stay where, at the point of contact. All right. Example of this is, basic insulating material like glass, wood, unless the wood is wet, or green wood. Because green's got a lot of fluids in it. Any kind of fluids, you're gonna conduct electricity. Unless it's ultra pure water, ultra pure water will not conduct electricity very well. But if there's any kind of, salt in it, seawater conducts electricity pretty well. Diamond, another form of carbon, but it's considered an insulator. And then in between these two are the semiconductors. So silicon, gallium arsenide, stuff like that, where your electronics are made from. They'll either conduct or insulate depending on the voltage that's applied to the little piece of silicon or gallium arsenide or whatever it is you're working with. And that's basically, if it turns from a conductor to an insulator, that means current was flowing and now stops. That's the on-off effect that all digital electronics function with. So your computer chips, solar cells, everything like that is based on the semiconductor effect. Now, I want to go through some more material with you concerning Charles Coulomb. He's the scientist that figured out the basic interaction of electrons and protons. Now, he didn't know anything about electrons and protons, but he knew plenty about static electricity, rubbing glass rods with silk and, metal or rubber rods with cat fur or rabbit fur. They could, in the days of Benjamin Franklin, they knew they were able to work with experimental equipment, primitive compared to today, but still enough to figure things out. He did. Charles Coulomb did for the electromagnetic interaction what Sir Isaac Newton did for the gravitational interaction. Now, he was a military engineer. He started life out down in Martinique in the Caribbean. 1776, the year of our independence. Long may it rain. He moved to Paris to eat some cheese and to become an academic scientist, which he was a good one, Charles Coulomb. He developed a device called a torsion balance that we still use today. It's not a balance that goes left and right, dips to the left or dips to the right, depending on what you put on the left, what you put on the right. It's a balance that's arranged to work with forces that work sideways, so that it, instead of torquing, clockwise or counterclockwise, as viewed from the side, it torques clockwise or counterclockwise as viewed from above. So it's a horizontal balance that twisted horizontally. It was hung from a very fine fiber, and every degree of twist was calibrated to a certain number of newtons of force. All right? So there's some force applied, some force toward you on one end and some force away from you on the other end. That's going to cause your object to twist if it's suspended in the middle. It's balanced and everything like that. Now, he was able to use that torsion balance to isolate the two physical factors that control the electromagnetic interaction. First, how much charge have you got? How much did you rub up the balloon on your shirt? Second, how far away is it? That's it. The amount of charge, Jihan, and the distance. That's it. Here's what it looks like. It's a pairwise interaction. So a red Q1 and a blue Q2. Okay, red positive, blue negative for Q2. They're going to interact. They're going to attract each other. And the only thing that matters is how much charge you have and how far apart are they. This is the force law. And notice, my wonderful students, it's an inverse R squared force. KQ1, Q2 over R squared. Just like gravitation. But this one's a little bit different because gravitation doesn't have two kinds of charge. There's only one kind of matter for gravitation. That's kilograms of mass. It's all the same. It always attracts. But for electromagnetic interaction, opposites repel. There's no repulsive gravity, but in electromagnetism, yes, there is. And the other thing that's different about it is that the charges are measured in coulombs. How much have you isolated? You rub a piece of glass against your shirt, a piece of rubber against your hair, you get some static charge going. How much have you got? Now, here's the force law up here. Okay? In the numerator are three numbers. Now, constant K is known as Coulomb's constant. And just like capital G in Newton's law of universal gravitation, that was a constant of proportionality. So is this. And you can look up the value for it. It's 9 times 10 to the 9 in the metric system. Newton meters squared per Coulomb squared. It basically converts the numerator, the square of two charge, or the square of charge, Coulomb squared in the numerator, and divided by meters squared in the denominator. That's not a Newton. But those are the only two things that electromagnetically generate Newtons. So K is the constant that converts from charge squared divided by meter squared to kilogram meter per second squared. Now, how does this force law accommodate repulsion? I want you to think of a negative and a positive charge. All right? Now, if I have a negative charge right here at the lectern, and then over here where Caroline is typing in, over here to my right, your left, if she has a proton, that would be this plus sign here. Okay, so this square bracket, that's the Caroline's charge. The regular parentheses, that's my charge, an electron. And so my electron is going to get, the force on the electron is going to get pulled toward Caroline. It's going to be towards the left, negative. And let's just say it's negative 10 newtons. You know, I have just enough distance to produce 10 newtons of leftward electrical force. It's an attraction. A negative and a positive attract. So the force on my electron here, my -1, is towards Caroline, off to the left. Now, if I take the parentheses and I take my electron out and I put a proton in its place, that would be like this. A +1 inside the parentheses. All right, so now the force, the electrical force on my charge in parentheses here, it's a proton, and Caroline is still a proton in the square brackets. So that proton in the square brackets is going to push my proton off to the right. So I should have whatever newtons I had leftward from having an electron here. If I put a proton here, I'm going to get the same number of newtons to the right. So a positive 10. All right, so here's how the force law changes the sign. It changes the direction. If you change the electron for a proton here, from a -1 in the parentheses to a +1 in the parentheses, over here, it changes from a -10 newtons to a positive 10 newtons. Now this second line of my equation block, that's an electron and a proton attracting each other. All right? But over here, it's a proton and a proton. The third line of my equation block, proton and proton repelling. So that's how this accommodates the whole idea of repulsion. All right, now I have some clicker questions for you I want to go over. Go ahead.
The R squared, like, will we actually use it?
Hold on. Go ahead.
How do we look this?
The distance, you mean in this equation?
Yeah.
I'm not telling you the distance, but I am telling you the size of the force. I'm telling you the numerator and the force, and we could figure out R squared if we wanted to.
But if you don't have to, even without K being given,
You could figure it out. But we're not going to worry about the distance. What we're worrying about here, Kane, is the switch from a leftward force in the second line to a rightward force.
you know, but if we have a positive electron and positive negative, what about the negative and negative?
Negative would behave the same way as this lower line here. Okay? Because negative times negative is still positive. So positive 10 newtons for that. Right, so if I had a negative here and Caroline switched to a negative, then we'd still have positive 10 newtons off to the right. All right, now I want you to make a sketch of this. We're going to do some clicker questions about this last few minutes. And in this diagram, I have 3 pairs of charges. Blue, in my computer work, blue is always for negative, red is always for positive. On the test, it'll be gray and white or black and white, but here it's blue and red. So the proton charge -1 or plus 1e, the electron charge -1e. All right, and here's my first question about this So I have 2 electrons in my top pair, a proton and an electron in my middle pair. My bottom pair, 2 protons. All right, so here's my question. Which pair or pairs, plural, have repulsive interaction? Do you have Darian's?
No, I do not. She didn't print it. She's gonna come by during your office hours to get it done.
Hopefully. Okay, 10 seconds to vote. 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, most of you got that one correct. D is the correct answer. Yeah, top and bottom. Brain burner. What direction is the net electric force on this proton over here to the right? It's got 2 neighbors, a proton, the nearest neighbor, and an electron a little bit further out to the left. What's the net electric force direction? Now, Kane, we're not figuring out the size of the force here, just the direction. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Go ahead and show this one, please. All right. So we have a little bit of a disagreement here. Majority voted for A, and A is correct. And the reason for that, go ahead and make a note. The reason that A is correct is the middle proton is closer. The middle proton pushes to the right. It has a bigger push. The electron is further away, so it's weaker. It's pulling to the left, but it's weaker. All right, so whatever the proton pushes to the right, the electron's going to have less than that. All right? Now, why are we even bothering with this? We're trying to figure out molecules. And for us, the idea of molecules begins in chapter 10. So chapter 10, read chapter 9 and chapter 10. No other homework until Thursday. So you're dismissed. Read chapter 9 and chapter 10, and we'll start here again on Thursday. You're dismissed.